Alright, so Euclid is a awesome dude back in the good old days, before, technology was invented. And he loved math so much that he just continued to investigate it and discover it and learn about it and compile it into one nice book for us. Alright, now, like I said, some of your answers might be different, depending on what source you use. How many of you guys used Wikipedia? Anybody use, I think it's Macworld or Math Open Resource? You might have been using it and not even realize you used it. That was actually the main resource I had to use for my history of mathematics class when I had to research mathematicians. Alright, so our first question. Euclid is known as the father of geometry. He's the man. Good. Alright, now when approximately did he live? Who would like to offer up their answer? Take Cameron.
300 BC.
300 BC, good. What are some other estimates we got? Okay.
Between the mid-4th and 3rd century.
Good, so 4th to 3rd century, good.
330 BC.
Good, 330 BC. Did anybody find kind of an ending date, a dying date from a lot?
The source I looked at said 365 to 300 BC.
So around there, good. Did anyone get mid-200s for the end of the day? Yeah? Okay. So your dates might vary, that's okay, just as long as you pretty much got it somewhere in the mid-300s, mid-200s-ish. All those answers that you said are acceptable. Now, if I asked you on a test when did he live and you said 1909, that would obviously be wrong. If you said 700 BC, that's a little too far off. So if you get between the 300s, 200s, that's good. All right. Did anybody happen to find out where he grew up? What country? What?
Alexandria, Egypt.
Egypt is where he lived as an adult, but not where he grew up. Amani? Greece. Very good. So if you didn't have Greece, go ahead and write down Greece.
A few articles I read said that he grew up, or was born in Alexandria and then went to Greece.
Okay, so yeah, so he grew up childhood days in Greece. Alright, so he grew up in Greece, which this was actually quite important for a particular reason. Question 4 is kind of a loaded question. Anybody have an idea what question 4's answer is? Why is this significant to his life? The fact that he was in Greece. Any thoughts on that? Lucy? Well, that is true. That is true. Any other thoughts?
Smart people live there then.
Yeah, it's kind of that. Someone last class had said a lot of philosophers were there. So the reason why this was most significant is because he was able to go to school there. Alright, so go ahead and just write that in. He was able to go to school. And so as a result of learning from these smart people, from these philosophers, that kind of influenced him and his mindset and his learning more and more about mathematics. Something interesting about mathematicians back in these older days that I learned when I was taking my history math class was a lot of mathematicians were also philosophers and astronomers. And likewise, a lot of philosophers were also mathematicians and astronomers. So it's kind of like those three things went together. It wasn't necessarily if you were a philosopher, you're going to be an astronomer, or if you're a mathematician, you'd be one of those. But a lot of times, those mathematicians also delved into philosophy as well as astronomy. All right, what do we have next? Oh, who did Euclid study under? Go ahead, Jake.
Plato.
Yeah. So Plato is a pretty prominent philosopher. He was a pretty smart guy. So Euclid actually studied underneath him. All right. And kind of cover this. What country did he live in as an adult? Egypt. So his schooling was kind of in Greece, but when he was an adult, he lived in Egypt. All right. Does anyone happen to know what university he taught at? Amy?
The Museum at Alexandria.
Good. So it was a school in Alexandria. We'll go with just basic, easy pronunciation of Alexandria. Won't be with the acronym. So University of Alexandria, and Alexandria is in Egypt. You want to make note of that. Okay. So I'm going to just tell you a little bit more about him that I have here. Alright, so there are no known records of the exact date or place of his birth, and little is known about his personal life. In fact, Euclid was a pretty popular name back then, so you might have started off finding information about a different Euclid that was not as, I hate to say important, but didn't do as much for geometry as this Euclid. So you might hear him referred to as Euclid of Alexandria to kind of denote which one we're talking about. So he taught mathematics in Alexandria, Egypt, at the Alexandria Library or Museum. And he wrote the most enduring mathematical work of all time, which is called, what's the name of his famous book?
Elements.
Good, The Elements. My husband has a copy of this. The Elements, and this is a 13-volume work. It is a comprehensive compilation of geometrical knowledge, so geometry, based on the works of Thales, Pythagoras. Okay, does that name sound familiar? Pythagorean. Good. Pythagorean theorem. There's also Pythagorean identity you'll learn about pretty quick. Plato, Aristotle, and then a couple names that I can't pronounce. And this was in common usage for over 2,000 years. Alright, so he's often referred to as the father of geometry. It is probable that he attended Plato's Academy and in Athens, Greece, and he received his mathematical training from students of Plato and then came to Alexandria. Just an interesting little tidbit. Alexandria was the largest city in the Western world and the center of both the papyrus industry and the book trade. So you'll actually learn a little bit about Euclid, I think, in your history class this year, when you guys learn about, I guess, reasoning. All right. Okay, let's continue on with the next question. Does anyone know why we remember him today? This is kind of a not straightforward question as well. Any thoughts on why we remember him today? Lucy? Yeah, so basically because he discovered geometry, compiled it into one good book for us. So, he wrote the Course of Geometry. So his book, The Elements, is work of all the basic geometry ideas. Basically what he did is, so he didn't invent geometry, right? Geometry was always in place, but he discovered it. Even before he discovered these postulates, it was already true that between any 2 points there is one line. That was already true before he discovered it. So he didn't invent geometry, he just discovered these truths about mathematics. And so his work is really important because what he did is he continued to investigate it and develop it more and more, and formally write it into one comprehensive book, kind of organize all these rules of geometry that he discovered. And so that was the kind of the go-to for anyone that was going to be continuing learning about geometry. It's kind of the foundation of geometry. It's the starting point. It's like the Bible of geometry, where it has the foundations, the startings of geometry. So it's kind of a big deal that the information we know about geometry was put in one single location and organized together. All right, so just a little bit more about that. So the Elements is divided into 13 books, which cover plane geometry, arithmetic or arithmetic and number theory, which that's something that you probably won't do unless you major math. Irrational numbers, you'll learn about that in Algebra 2. Or sorry, not irrational. Irrational, you've already looked up. And solid geometry. So you'll hear our class referred to as Euclidean geometry, plane geometry, flat surface plane. Euclid organized the known geometrical ideas of geometry, starting with simple definitions, axioms, which are form statements called theorems, and set forth methods for logical proofs. And you'll find in our class we actually do a lot of proofs. We'll be doing them every single unit. So it's really important that you know those definitions that we got from our vocab sheet and know the postulates and theorems we're going to learn today, because we use those to prove other postulates and theorems. He began with accepted mathematical truths, axioms, and postulates, and demonstrated logically 467 propositions in both plane and solid geometry. That's a lot of And then it goes on to say one of the proofs was for the theorem of Pythagoras, proving that the equation is always true for every right triangle. B squared plus B squared plus C squared. And the Elements was the most widely used textbook of all time, has appeared in more than 1,000 editions since printing was invented, and was still found in classrooms until the 20th century, and is thought to have sold more copies than any book other than the Bible. So it's well used around the world, and our course of high school geometry here in the U.S. is basically built upon what he found for us. All right, let's talk more about it. We're almost done. All right, does anybody happen to get what are postulates or axioms? Go ahead, Lonnie. Yeah, statement that's self-evident, that's a good way to put it. So it's a statement that can't be proven, but we accept it as true. It's kind of like that basic foundation. We briefly talked about this with our vocab last time. So statements not proven, but accepted as true. And number 11, where can we find his book today, or the revised version? If you wrote Amazon, you are correct. You can buy it off Amazon. That's not what I was looking for, but you're right. We can buy it from Amazon or in a bookstore. What I was looking for is that it's actually, the revised version is our high school geometry textbook. Did you write that down? Awesome. Okay, so if you wrote something else, just sneak in there that we're talking about, it's our textbook today. So just trying to convey that concept that our geometry that we're learning is based upon what Euclid discovered for us many years ago. Remember last year, it's like Amazon's like, well, yeah, you're right. I said that on Amazon. Alright, so again, what we are learning about in our high school geometry class is Euclidean geometry, and it's really based on that parallel postulate. And like I talked about, there's hyperbolic geometry or non-Euclidean geometry, and you probably won't be able to find unless you major in it. Okay. Now, it says, what are the 5 postulates of Euclid? Now, as we talked about, Euclid had discovered 1 million postulates. But there are a few postulates that are kind of the starting points, the building blocks. So your answers for this bottom part might be different. That's okay. You don't need to write new ones down. And our notes for today, we'll write out the 5 that we are starting with. Okay? So this is just for you to kind of look at and compare to what you had. The first one, and I assume probably all of you had some version of this, is that any 2 points form a straight line, or through any 2 points there is one line. Exactly. We kind of discovered this. And honestly, these postulates that we're writing, that I have up here, are ones that we've been using, that we've kind of discovered as we talked about our vocab and scenarios of which lines and things to intersect. Alright, our next one is an infinite number of lines can be drawn through one point. Again, it might be worded differently how yours is, which, if we think about that, take a point, I can draw this line through it, I can draw this line through it, pretend that intersect that point. That line here, I can draw an infinite number of lines. Alright, does anyone have a postulate about a circle? Just in there somewhere? Alright, so the next postulate is that a circle can be drawn with given a point and a radius. And that point is really the center that we're talking about. So basically, you give me a center and a radius, and I can draw a circle. Alright, and then this one you might have had something different, is that all right angles are congruent. That's actually the right angle congruence theorem is one of the theorems that we're learning today. And then the last one, parallel postulate, there are quite a few super mathy ways to put this. So we kind of try to tone it down for us. Given a straight line and one point not on the line, only one line can be drawn through that point that is parallel to the first line. So if I have a line, pretend that's straight, and a point not on the line, doesn't matter where I put that point, I can draw only one line through that point that is parallel to my first line. This little notation, little arrows like that on the line indicates parallel. I could do that even if I have the point, say down here. Only one line can be drawn through it that makes these parallel. So that's our parallel postulate. Again, don't worry if you have different ones here. On our notes today, we'll write out the 5 that we're using as our starting points. Any questions on Euclid? You have to let me know when you learn about it. Okay, So let's go ahead and dive into our notes. And you'll see that today we're learning about the segment and angle addition postulate. These were at the bottom of our vocab sheets that I said we were going to save until later, so we're learning that today. If you want to add it to your vocab sheet, you're more than welcome to. But we'll write it out for you. Awesome. Another one? I keep forgetting to grab your summer signs from you. So if you would pull those out, make sure your name's on it. If you have a sticker, I'll go ahead and pass that around. If you don't need it, just pass it to the next person. Once you've got your summer assignment kind of all compiled together, just pass it forward. If you forgot to do it, just bring it next class. Oh, yes, I want your work with the time of you. Will, did you have a question? I thought I saw another hand. So again, once you have that summer assignment all compiled together, make sure your name's on it, pass it forward.
Yesterday, but I stapled all together.
That's okay. I'll figure it out. I saw some were turned into the pile with the quizzes. So you'll see that I went ahead and passed your homework out to you because we'll go ahead and use some of those problems as kind of our example problems as we go through and learn our different postulates. But your homework will be to finish that packet, whatever we don't do. So notice it is a longer homework assignment, so do not wait until the last minute to do it. But we will be doing some of it in class to kind of practice those concepts. Also, don't forget, if you look at your assignment sheet, what do we have next class? Not a test, a quiz. But you make everyone nervous if you do that. It's a lot shorter and over only half the material. Okay, so next class is a quiz. This is where it'll actually be geometry, no longer your algebra quiz. So it's going to be over our geometry vocab we've done, the postulates that we're doing today. We'll spend next class going over the homework and any questions you have with it, but make sure you're coming prepared with those questions. Okay. I'm actually going to go ahead and put the answer key to tonight's homework on Blackboard. So as you're working through, if you get stuck somewhere, try it first, give it an honest effort, but check your answers with that key, see if you can find where you made a mistake, and hopefully that'll iron out some issues so that next class we can go through questions quickly. Yes?
Much of the vocab is going to be tested.
Everything we've learned. So it's everything from lesson, yeah, I told you got to do the vocab right away. So anything we've learned 2 classes ago, last class was just more practice, and then today, so lessons 2 and 3. Welcome to Geometry Honors. All right, so let's take a look at our notes for today, where we actually dive into postulates and theorems, and you do need to know these. You need to be able to apply them to certain scenarios. Now, you are going to be expected to recall these postulates and theorems. Some of these have names, such as the segment addition postulate. And when it has a name, you can just refer to it as the segment addition postulate. But if it does not have a name, such as postulate 1 here, then you're going to have to state what it actually says. Now, if you ever forget the names, that's fine. Just state what it says. And you don't have to have the words verbatim, just as long as you convey the same idea, right? So our segment addition postulate, we have here segment AC, and B is on there. Notice that these points are collinear. this is important for your segment addition postulate to hold true. Okay. For your segment addition postulate to hold true, they must be colinear. Okay. Now our segment addition postulate is kind of self-explanatory with the title there. We have a segment and we're adding stuff. So you'll find these postulates are pretty easy to understand. Alright. So we see we have segment AB, segment BC, and segment AC. Well, my segment addition postulate says the measure of segment AB, remember our notation for measure of, distance of, length of, we do not draw that segment over the top. So the measure of segment AB plus the measure of segment BC is equal to the measure of segment AC. Alright? So basically, you take the pieces up and together, you get the full. Okay? Alright, now this is what you'll see most often. The segment addition postulate is written out like this. But we could change it up a bit. Would you agree that I could subtract the measure of AB over to the other side and it would still hold true? Remember, these are just measures. They represent a numerical value. They represent some number. Whether we know it or not, they represent some number. So I can subtract that over to the other side. So I could say BC, the measure of segment BC, is equal to the measure of segment AC minus the measure of segment AB. I just simply subtract that over. So in other words, what I'm saying is this chunk is the whole thing minus the piece I didn't want, right? So if you see this notation in a proof, we'll still call it segment addition postulate. It's just another format of it. But this is the most common way that you'll see it, and probably the most common way that you'll write it. So that's just forms. Questions on that? Okay. So go ahead and take a look at that lesson 3 homework and the very first problem. So if PQ equals 7 and QR equals 10, then PR equals what? Alright, so the measure of PQ is 7. The measure of QR is 10. What's the measure of PR? Ooh, you guys are geniuses. Awesome. Okay. Now let's take a look at number 23. It says if the measure of PR, the whole hunkin' thing, is 25. Looking at number 3.
Oh.
Sorry, I skipped number 2 because it was too easy. Did I say number 23? Ooh, okay, let's just go to 3. So for number 3, it tells us that the big whole thing is 25. And PQ, the measure of PQ is just 12. So then what would be the measure of QR? 13. Now, what you did, that's the wrong spot. What you did is technically what our second statement was here. We did that subtracting part. And really what we're doing is using that segment addition postulate just in our head. So, for example, number 3, we could start off by saying the measure of PQ plus the measure of QR equals the measure of PR. We know that PR is actually 25. We know that the measure of PQ is actually 12, but we don't know QR. So then we solve, subtract 12, and that's how we got the measure of QR was 13. So you were doing that segment addition postulate in your head. I don't expect you to write this all out when it's a quick, simple, easy numerical one like that. But we're not always going to give you just straight numbers that you add and subtract. You might have an expression given to you. For example, with number 6, you can see that instead of giving us the actual measure of ST, we get an expression for it. So this means that this measure we could write as 3x plus 3, and this measure we could write as 2x plus 3. Okay? So you might need to set up an equation to start off with, but obviously 1 through 5, you can probably do that. Okay. Questions on that? Okay. So let's go and take a look back at. Okay. All right, angle addition postulate. Very similar concept, except now we're dealing with angles. And notice that these two angles are adjacent. And this is important because the angle addition postulate only holds true if the angles are adjacent. Alright, so we could label these angles angle ABD, angle DBC, and angle ABC. But you'll notice that we went ahead and put a number 1 and number 2 in there. That's to make it easier to label our angles. So angle 2 is the same thing as angle DBA. And angle 1 is the same thing as angle CBD. But it just makes it a little bit quicker to write. So you'll see we do that a lot. If we give you a picture with the angles numbered, then go ahead and use those numbers. We're just trying to save you time with the writing. Right. So my angle addition postulate here. The measure of angle ABD. Oh, I said use the numbers. I'm sorry. The measure of angle 1. See how much faster that was. And remember, this is our notation, measure of the angle, plus the measure of angle 2 equals the measure of angle. Now we're going to have to use the actual letters here. The angle ABC, or you could say CBA. Okay, so two adjacent angles added together gives you the whole thing. Now, just like before, we could have subtracted something over and written another form of it. Same idea with angle addition postulate. But this will probably be the most common way to use it. Yes?
Is it okay if you like write the letters in?
Do you have an emergency? In office, do you have an emergency?
No. I'm sorry. Someone must have hit the button.
Okay, thank you.
Thank you. I got so confused. I thought that was just an announcement. Guys, be careful you don't hit that button on the back because then they sound like joking. Yeah. Okay, so careful that when you stretch, you don't make them think that there's an emergency or confuse us all. That's okay. I got confused. I'm like, there's an emergency? What's the emergency? What do we need to do? I thought we'd have to do a fire drill out in that rain. All right. Okay, so yeah, we can use the letter. So
No, I meant like
sorry.
already can we like write the letters in like lowercase or does it have to be in capital?
That's a good question. Capital. If it's presented to you in lowercase, you can write lowercase, but typically it'll always be written in capital. Now, you might have seen when you're reading through sections 1, 2 in your textbook that they said a line, or even like a line segment. We said that this could be written as line AB or line BA. But sometimes what we'll do, so we number angles, but for lines instead of numbering them, we'll use a lowercase cursive letter. So we might call this line L, in which I would just say line L. So you might see like that, you would just then say line L rather than L with an arrow at the top. Does that make sense? But we can, even though you didn't notice this, we can go ahead and say measure of angle CBD plus the measure of angle DBA. Alright, any questions with the angle addition or segment addition postulate? Okay, so let's again take a look at our homework sheet. And this time I want you to flip on the inside to number 18. So number 18, you'll see they didn't give us just straight numbers, they gave us some expressions. And unfortunately we have S, which is sometimes hard because it starts to look like a 5. So bear with me if my numbers start to look like letters. Alright, we have RZT, the big angle given to us, and then they gave us an expression for RZS and TZS. So let's go and just set up what our angle addition postulate would be. So the measure of angle, I'm just going to start with RZS. Of RZS. Remember, your vertex needs to be that middle letter. Plus the measure of angle ST ZT. Or again, you can flip those numbers, the letters down. My goodness, are we all having grammar issues? Do you have your syllabus, TA syllabus sign-off sheet thing? What do we call that again? Past paper?
When we have our agendas.
When they come in. No, they didn't.
I don't know that. They didn't like it.
No, they order it before the school year starts, but they're waiting until the schedules are all set in place and they get all the information.
Do you have another one of those papers?
I do not, but I can help you. You got it in your TA box.
Yeah.
I can help you. All right, so we have angle of RZS, but measure of angle SZT, and this is equal to that whole hunkin' thing, the measure of angle RZT. All right, so piece plus piece equals the whole thing. Let's fill in what information we do know. What is angle RZS? What do they tell us that is? 3x. What is SZT? 8x. Good. So notice we wrote it a little different. They said TZS, but it's the same thing. TZS SZT. And what is the measure of angle RZT? 110. All right, go ahead and solve that. Tell me what you get for S. What do we get for S?
S equals 10.
Good, S equals 10. Okay, but did they ask us for what S was? No. So in geometry, you'll see that a lot of times the questions, and especially in geometry honors, they ask for something beyond what just you saw for. So they're not just asking for S, they want to know the measures of angle RZS and angle TZS. So what do we do then? How do we find those? Very good. They gave us expressions. We now know what S is. Just substitute in. All right, so then we can go ahead and declare that the measure of angle RZS, since it said 3S and we know what S is, what would that mean? 30. Good. And technically we're dealing with degrees in here. We should write degrees. I'm really bad about doing that. I won't be super strict on it, but we should be writing degrees. There is another way to measure angles, and it's in radians. You'll learn about that in pre-calc, but we're dealing with degrees. All right. And then measure of angle TZS is going to be what? 80 degrees. All right. And we should double check. Does that add up to be the 110? Yeah. So pretty basic now. You might feel more comfortable right now writing that first statement, but it's not really necessary. You can go ahead and just write the equation here where you have those, we're just going to substitute in those expressions. But when we do proofs, you will need to write out this full statement, the very first one, where you have to write out all the details. All right, questions on that? All right, so let's go ahead and go back to the notes. So that was segment addition and angle addition questions. Again, pretty basic ideas. Okay, so now I'm going to make you write in some of these postulates here. So the beginning postulates of geometry. And these are slightly different from the Euclid's ones that we talked about. They've been adjusted for high school geometry, and these are what we're considering our starting points, our building blocks. All right, now remember, postulates are statements that we accept to be true without proving it to be true. All right, our first one that we're going to state is that through any 2 points, there is exactly one line. So through any 2 points, there is exactly one line. Through any 2 points, there is exactly one line. And again, we've already kind of investigated this and talked about it. If we draw 2 points, regardless of how they are positioned, one line can be drawn. All right, postulate 2. And I want to be careful, this is not the name of it, this is just us labeling 1, 2, 3. So you can't call this postulate 1, you'd have to say there are any 2 points, there is 1 line. All right, postulate 2, our second one. If 2 distinct, meaning different, lines intersect, if 2 distinct or different lines intersect, then they intersect in exactly 1 point. When they intersect in exactly 1 point. So if we have 2 lines that do intersect, I mean they're not parallel, and this is talking about 2 coplanar lines, it's technically 2 coplanar lines, then they intersect exactly 1 point. Pretty basic again, but I'm just going to draw it out. Let's go and draw, we'll call this line L, and draw another line intersecting it. Let's call this line K. And if we look, they intersect at a point. What shall we call this point? Let's call it P, or point. Alright, so if 2 lines do intersect, and we specify that they're different lines, because if it was intersecting everywhere, then it would just be the same line, right? If they are 2 different lines that intersect, it's just a 1 line. Alright, 1 and 2 were pretty basic. Alright. The third one. Taking this and extending it to planes. If 2 distinct or 2 different planes intersect, then they intersect in exactly 1 line. If 2 distinct planes intersect, then they intersect in exactly 1 line. So again, if 2 distinct planes intersect, then they intersect in exactly 1 line. And again, we've already investigated this and talked about it. We talked about this ceiling in the front wall intersecting at that line there. We looked at a book. If we fold kind of the pages around, the binding is the line at which they intersect. You can just simply take your hands and make them 2 planes that intersect along that line. So we'll draw a picture for this. I feel like it's kind of hard to draw this because it's going 3D-ish, but we'll do our best. Let's draw a plane. Here we go. Plane. Number of planes continue on in all directions forever. And we're going to draw another plane intersecting. Right, which means that this plane is actually behind it. Let's do that dotted. This one. There. So do your best to draw the 2 intersection planes. Alright, and if we look here, where they intersect is going to be along this line. Again, just kind of like our hands intersecting. Alright, now again, this is if 2 planes do intersect. And that's talking about specifically 2 planes. We talked about different cases for 3 planes intersecting. We said 3 planes could intersect at a line. If I just drew another plane cutting through there. Or we said at a point, kind of like the corner of the class. Plane, plane. What? Question on this first 3.
So is there also like an infinite amount of planes?
Yeah, so infinite amount of planes can go through a line. Yeah. So it's kind of like a continuation of, oh wait, we haven't done it yet. Our next one, nope, okay, later we're going to be learning that through any 1 point there's an infinite number of lines. Same idea, through any 1 line there's an infinite number of planes. Okay, other questions. So let's take a look at our 4th postulate. Through any 3 non-collinear points, there is exactly one plane. So through any three non-collinear points, they're not in a straight line, there is exactly one plane. So again, through any three non-collinear points, there is exactly one plane. And again, we kind of already talked about this, how that third point kind of establishes the slant of your plane, if you would. So there's not really anything fancy to draw for this. We're just going to go ahead and draw 3 points. Oh, look, here's the plane that contains it. It's your sheet of paper. But we've talked about it more fancy fashion up here. If I take my fist here, I can have a plane that slices through this. Alright. And our last one, our linear pair postulate. So this one actually has a name. You can call it by name, the linear pair postulate. We actually use this the entire year long. We'll be using it in our proofs the whole year long. We'll use it particularly when we get to unit 2 or 3. We're dealing with parallel and perpendicular lines, or really just intersecting lines. Alright, so the linear pair postulate, and we've already talked about this too. We've already kind of discovered this when we did our vocab. But if two angles form a linear pair, then they are supplementary. Or in even shorter words, linear pairs are supplementary. If it's a linear pair, then it's supplementary. So that's our linear pair postulate. If two angles form a linear pair, then they are supplementary. Imani? Oh, did I never sign yours? I'm sorry. So I want you to go ahead and draw an example of linear pairs on your piece of paper there. Alright, so if we have a linear pair, remember linear pairs are angles whose non-common side forms opposite rays. So if this is the non-common sides forming the opposite rays, kind of makes that line that straight angle. And they have to be adjacent. So linear pairs have to be adjacent and have this kind of property where they form that line, if you would. So let's just call this angle 1 and 2. And by just looking at it, we can see that because those non-common sides form opposite rays, that has to form that line, which means it forms that straight angle, which means they have to add up to be 180. Alright, and remember, supplementary means it adds up to be 180. So, be careful though. The definition of linear pairs is what allows me to say angle 1 and angle 2 are linear pairs. So the definition allows me to establish they are linear pairs, just to simply state it, to see the picture and say angle 1 and angle 2 are linear pairs. But it's the postulate that allows me to say that they are supplementary. So it's the postulate that allows me to say angle 1 and angle 2 are supplementary. So be careful with that when we get to proofs. It's going to be very particular about using this property. Questions with that? Okay. So let's go ahead and take a look at what we have on the back side. So these are some more theorems. The right angle congruence theorem we've already kind of talked about. The right angle congruence theorem says all right angles are congruent. Pretty basic, straightforward. All right angles are congruent. Remember that equals with the squiggle is your congruent symbol. And keep in mind, I know we wrote this on our vocab last time, but keep in mind that this is congruent. And we use this to talk about the figures or the pictures. And then we use equal when we're talking about the measure, or the distance, or the length, or the measure of the angle, the measure of the segment. And later on we'll talk about kind of going back and forth between those. Alright, so right angle congruence theorem, all right angles are congruent. Alright. Now, congruent supplements theorem and congruent complements theorem, they're very similar. I feel like congruent supplements theorem everyone forgets about, and it's actually a very beneficial and helpful theorem. So make sure you're really studying your vocab and these theorems and postulates, and that you can know how to apply them. Alright, so congruent supplements theorem states, I want to make sure I get it perfect for you guys. Alright, if two angles are supplementary to the same angle, so two angles are supplementary to the same angle, so again, if two angles are supplementary to the same angle, then those two angles are congruent. And those two angles are congruent. Remember, congruent means it's that same size, same shape. So in other words, they have the same measure. But the congruent supplements theorem tells me that if two angles are supplementary to the same angle, those two angles are congruent. Alright, so let's just go ahead and draw a picture to go into this and we'll kind of outline what this is. Alright, so let's have here angle 1, angle 2, and angle 3. So I've got angle 1, angle 2, and angle 3. So if two angles are supplementary to the same angle, so for our little example here, if angle 1 and angle 2 are supplementary, I'm just going to put sup with an extra key. And likewise, angle 1 and angle 3 are supplementary. Okay, so using our picture that we drew here, this is just an example. If we know that 1 and 2 are supplementary, what does that mean, supplementary again? Yes, they add up to be 180. And I also know 1 and 3 are supplementary. Then by this congruent supplements theorem, it must follow, so then, it must follow that angle 2 is congruent to angle 3. So if they are supplementary to the same angle, and notice here, 2 and 3 are supplementary to the same angle, they're supplementary with 1, then it must be that these two are congruent. Now, that might sound a little crazy, but let's start with some numbers and you'll see how logical this really is. Let's go ahead and just say angle 1 is, for simplicity's sake, 100 degrees. Okay, let's say that angle 1 is 100 degrees. If 1 and 2 are supplementary, what does 2 have to be then? Okay. And if it's also true that 1 and 3 are supplementary, what does 3 have to be? 8. Well, as we can see, 2 and 3 must be the same thing. The reasoning for this is that the fact that they're supplementary means they add up to be 180. So they're going to be adding up to the same amount, 180. And angle 1 stays the same, it doesn't change. So angle 1's value doesn't change. What they add it to doesn't change. So 2 and 3 have to be the same to maintain that same equation. Okay? So if two angles are supplementary to the same angle, then these two must be congruent. Questions with that? Alright. So congruent complements is going to be very similar to this. If two angles are complementary to the same angle, if two angles are complementary, if I can squeeze that in there, to the same angle, two angles are complementary to the same angle. What does that mean, complementary? Good, adds up to be 90. Then, those two angles are, can you guess what it is? Congruent. Good. And it's the same thinking, the same idea, the same process there. Just instead of adding up to be 180, it adds up to be 90. So congruent supplements, congruent complements. Supplements, you see that word supplementary, and so the word congruent. Complements, kind of see that from the word complementary. All right, questions on those ones? Those might be the most complicated ones. All right, vertical angles theorem. We already briefly talked about this on our vocab day as well. We kind of already investigated and discovered this for ourselves. All right, so let's first talk about what vertical angles are. Vertical angles are angles whose sides form opposite rays. And so what that ends up looking like is some type of that. So angle 1 and angle 2 here, their sides are opposite rays. Sides are opposite rays. So angle 1 and 2 are vertical angles. Okay. Now, that's what the definition tells us. Again, be careful with that. The definition is what allows me to say angle 1 and angle 2 are vertical angles. Okay. The definition is what allows me to say that. Let me scoop this up. Get out a little bit better. So again, the definition of vertical angles is what allows me to say angle 1 and angle 2 are vertical angles. But what the vertical angles theorem tells me, and we'll be using this one all year long, is that vertical angles are congruent. Which we saw that from our picture here, and I think we're actually proving this later. But it's pretty clear from our picture, angles 1 and angle 2 are congruent. And likewise, we could go ahead and throw in angle 3 and angle 4, right? Angle 3 and angle 4 are going to be congruent. So really what this theorem says is if angle 1 and angle 2 are vertical angles, and you're going to see me abbreviate vertical angles as just VA. I don't mean Virginia, I mean vertical angles. You'll see me write VA theorem rather than vertical angles theorem. That's fine for you to do that as well. So if angle 1 and angle 2 are vertical angles, as we can see from the picture, then angle 1 is congruent. Now again, you've got to be very careful. It's the definition that allows me to look at the picture and say, hey, 1 and 2 are vertical angles. But it's the theorem that allows me to then say angle 1 is congruent to angle 2. Again, in proofs, we're very thinking about that. All right. Likewise, angle 3 is congruent to angle 1. All right. Questions on that? Okay. And then our last two kind of go hand in hand. These are actually definitions, not theorems and postulates. All right. So definition of congruent segments. Let's first start off by drawing some congruent segments. Alright, so I've got segment AB. And let's go with segment LT. Alright, so we have segment AB, segment LT, and we're going to go and put on this mark here, a little tick mark or a dash like that. Means congruent. So when you see this, what this indicates, what the picture indicates, is that A, B, and LT are congruent. If you see two dash marks, 2's go together, 1's go together, 3's go together. So that means anything that has that one dash mark within the problem is the same, or has the same measure, it is congruent. All right. So the definition of congruent segment says if AB, the segment AB, is congruent to segment LT. So if the figures are congruent, we're going to go put in parentheses figures or pictures. Because remember, congruent always goes with the figures. So if our figures are congruent, then we can go ahead and say that the measure of segment AB is equal to the measure of segment LT. That's measures that we're talking about. Measure or length or distance. So if I know that two segments are congruent, I can say their measures are equal. If I know two measures are equal, I can say their segments are congruent. It just allows you to go back and forth. And this is important because in proofs, sometimes it starts off with a congruency statement, but it asks the student to prove that they're actually equal. So at some point, you have to make that transition. Also, you'll notice that our segment addition postulate, it is in the form of measures equal. I can use that definition, though, to convert this to say segment AB plus segment BC is congruent to segment BC. So we can use that to kind of convert it back and forth. All right, and then it's the same thing for our angles. So definition of congruent angles. Again, let's go ahead and just draw a couple of congruent angles here. I'm going to go with angle ABC. And as best as I can, let's go with X, Y, Z. So we got two congruent angles. Now the notation to show that angles are congruent is an arc. And again, the same number of arcs means they're congruent. So this indicates that these are congruent. If they both had two arcs, that would mean that they're congruent. If this had one arc and that had two arcs, then they're not congruent. They're different values. All right. So it's going to be a similar thing. If angle ABC is congruent to angle XYZ, then we can say their measures are equal. And the measure of angle ABC is equal to the measure of angle XYZ. And again, notice congruent is used for figures or pictures, and equal is used for measures. So again, that allows you to go back and forth between. All right, questions on that? So I've thrown a lot of postulates at you today. You want to be familiar with them enough to be able to apply them and use them. Segment and angle addition postulate basically says the pieces add together gives you the whole. Our beginning postulates are kind of just our investigation with lines and planes as it was. But this last one, the linear pair postulate, is really important. That linear pairs are separate. Notice again that they are different from just the definition that states that they're linear pairs. And then on the back side, our right angle congruence theorem, all right angles are congruent. Congruent supplements and congruent complements are similar. And they're set up. Vertical angles theorem, again, be careful. The definition is what allows me to look at the picture and identify them as vertical angles. The theorem is what allows me to state that they are congruent. And then we have where we can go back and forth between congruent figures, measures. Questions on what we've done here? Okay. So on our lesson 3 homework, let's go to number let's go to the front side, I think, of this one. Okay, so let's take a look at number 6. All right, so again, here we see this notation with that one dash mark. This indicates that the measure of ST is equal to the measure of TU, or segment ST is congruent to segment TU. That allows us to pull that from the picture. Whereas here we see our angle measures here. So this allows me to say that angle GXF is congruent to angle IXG. Okay, so that's that notation. All right, so number 6, they give us that the measure of ST is 3x plus 3. And the measure of TU is 2x plus 9. So it says, what is the value of ST and what is the value of TU? What are your thoughts? How can we go about solving this? Come on.
Well, first of all, if both of those are congruent, then it would be the same if you said 3x plus 3 is equal to 2x plus 9, and you can solve from there.
Very good. So we're applying that definition. Okay, so we're applying that definition. We can pull from the picture here that ST is congruent to TU. And from that definition, we know that the measure of ST is going to equal the measure of TU. Which means we can just take those expressions and say 3x plus 3 equals 2x plus 9. From there, we can solve for x and find those values. Now again, you don't have to write these statements up here. If it was a proof, we would need to. If you're able to look at this and go and just set up your equation here, that's fine. But I do want to see an equation set up. And then I want you guys to go ahead right now, go through and solve and see what you get for A and B. If you finish that, go ahead and do number 7. But I want us to start off figuring out number 6 and see what we get. And again, once you get your answer, feel free to check with someone nearby, see if they got the same thing. So again, once you get 6, check with someone, and then go and move on to 2. You didn't miss any notes. The class that you missed.
No, we're not.
No, here. Because once you have it, I'll get it.
1, 2.
The next one, did you get the 3?
Alright. For number 6, what did we end up getting for our x value? Okay, 6. So then what did we get for the measure of ST?
21.
Good. So be careful. Make sure you write this in proper notation. Again, I will be very strict on this. We're talking about the measure of ST. We read this as what is the value of the measure of segment ST. So we come back with an equal sign. And then what do we get for our measure of segment TU? Okay. Which you could have either substituted back into the equation or use your noggin, work smarter, not harder, and say, well, if they're congruent, their measures are equal. Alright, so now if we set up number 7, what is going to be my equation set up for number 7? Good. X plus 3 equals 4x minus 6. Alright. I won't spoil the ending for you there. Alright, so again, here with this picture, we can see ED is congruent to DB. But since these are 2 tick marks, then it's going to be AD is congruent to DC. It's not the same as our 1 tick marks. It might end up that when you solve, you find they are the same. But from the picture given to us, we're going to assume they're not the same unless we find out otherwise. Okay, so that's kind of that example of the difference in the tick marks. Okay, any questions on that? So again, make sure you complete the rest of that 4 homework. I'll go and put that key up on Blackboard so you can compare. Next class, we'll have a short quiz over this material and the vocab, so really make sure you're studying that.
I